Right, we are going to bring this chapter 2 to a close here today. We've been talking a lot in this section 2.2 about normal distributions. Okay, that's that standard normal curve, how to find the areas between values or to the left or to the right, or if you're given the area, how to find the boundary value. But I've been saying that a problem has to give you the rights to be able to use those normal features on the calculator or to use that standard normal table. It has to mention that the shape is normal, okay? So I want to talk a little bit here about, when is it that you can use these normal calculations, like normal CDF, inverse norm, and table A. Okay, first and foremost, this has only been our situation right now, is you can use it if the problem tells you that the distribution is normal, okay? And we've been lucky enough that up until this point, it's just kind of handed that to us on a platter, if you will, okay? But we need to come up with some ways of what if the problem doesn't just say the shape of the distribution is normal, how could we possibly conclude that it is normal and then move forward with some of these calculations, okay? So here's some options. We have 3 of them, okay? Option number 1, this is ways that we can assess normality. Okay, ways that we can assess normality here, okay? Number 1 is to take our data set. If they gave us the body of data, we could put it into L1, list 1 on our calculator. We could make it into a histogram, or by hand we could make a dot plot, or we could make a stem and leaf plot, kind of turn it to the side, and we'd be looking for the shape, okay? If you were to plot the data, and what you're looking for is just seeing if the shape feels like it's approximately or roughly symmetrical and bell-shaped, that could be a reason for us to continue to move forward and assume that it meets that normality condition, okay? A second possibility, and you'll see this with an example that we're going to do here, is just to check to see whether it feels like the data falls in that empirical rule, which is the 68, 95, 99.7 rule, okay? And typically what that means is that your max and your min values, they should be out about 2 or even 3 standard deviations from the mean, and they should be equidistant from the mean. So in other words, it would not make sense if you say you had a graph and you said, here's where the mean is, okay, and over here is my max, but then right here is the min, okay? See why that doesn't really make sense? Because, if the max is here and the min is here, I would expect the mean to be more in the middle. So that doesn't make a lot of sense here if it's actually normal, okay? And then our last option would be to make something, which I'm guessing that you've never been introduced to this before. You would make something called a normal probability plot, okay? And I'm going to show you how to do that here today. But let's just start with example number 12 here, okay? And if you look at the information they give you, it says, given the following data, is this distribution roughly normal? Okay, so they're not giving us the body of data, they're giving us just a few little snippets here, what the mean is, the standard deviation, the min, and the max. Okay, now I have this curve drawn here, and this is assuming that it is normal. Okay, so let's just pretend that maybe this set of data is normal. If it is, then the mean, 60, should fall right there, okay? And I would expect the min and the max to be out at least 2 or 3 standard deviations from the mean, because if you go out 2, then you've included 95% of your data, and the min and the max should be the farthest ones out there. If you go out 3, 99.7% of the data, okay? If I go 1 standard deviation to the left on this, I'm at 55. If I go out 2, I'm at 50. And if I go out 3, I'm at 45, okay? My min is right there, okay? That's fine. That's it. That's maybe about where I expect it, somewhere in the 2 to 3 standard deviations from the mean, if it's normal, if the distribution's normal. Okay, now, if I count 1 standard deviation to the right of the mean, then I go 2, and then I go 3, look at where the max is. The max is like right here at 66. This mean doesn't feel like it's centered very nicely in the middle of the min and the max, okay? So this is kind of evidence here where maybe I would say, no, this is not approximately normal because the max, this max should be further out. It should be out 2 or 3 standard deviations from the mean. Also, I could make a note that the max is not a similar distance to the mean as the min is, okay? All right, so let's look at a normal probability plot, okay? This is something that you're not going to make by hand. We're going to make these on the calculator, but I want you to understand what it is and how to use it, okay? Because our third way of kind of assessing normality is to make a normal probability plot, and then you have to know what to look for in that plot, okay? So what these are, a normal probability plot, okay? These plots are constructed when you take each piece of data and you plot it against its corresponding z-score, okay? So in other words, let's say you surveyed everyone, you asked them, what is this representing? Survival time in days, okay? So you would have the data, the survival time is your x variable, but then if you change that into a z-score, the y coordinate that goes with that is the z-score of that particular x value, that particular set of data, okay? The z-scores are on the y-axis. The observations are your x variable. So here we have a histogram, okay? You can clearly see that the shape of this histogram is not normal, okay? We would definitely be able to tell that by looking at this. I want to show you how this data looks in the context of a normal probability plot and how you'd be able to tell if you only had this to look at that the data is not normal, okay? When you are plotting and making a normal probability plot and you're plotting each observation against its z-score, if it's normal, you would expect this to be relatively linear. It doesn't have to be an exact straight line, but if you start to notice that this is curling to the right, that means the original set of data was skewed to the right. So I just want you to make that note here. Just say curving to the right means the data is skewed right, okay? Incidentally, had the data been skewed to the left, then I would probably expect my normal probability plot to maybe do something like at the end, it starts to take on this little curve that starts to go to the left, okay? All right, so let's look at an example here. It says here, if the points in your normal probability plot lie close to a straight line, then that indicates that your data set is normal, okay? So here's what you're looking at. When you look at the normal probability plot, does that scatter plot feel like the trend is pretty much a straight line, okay? They don't all have to be in an exact line, but there's not an evident curl happening, okay? It needs to be the systematic deviations of basically a straight line, okay? So let me scroll on down here. We'll look at this example. There's a great normal probability plot there on the left pictured that you can kind of see that this plot would indicate that the original set of data was in fact linear or normal, or at least approximately normal. So let's pretend that you go and you survey a group of students, let's see, not very many, 2, 4, 6, 8, 9 people, and you ask them how many pets do you have, okay? Now I purposely made this dot plot perfectly normal, okay? So we know by looking at the dot plot that this actually is a normal distribution here. Three people said they had 4 pets, 2 each for 3 and 5 pets, and 1 each for 2 and 6. So here are your responses. These are the observations, okay? If I run one variable stats with this in L1, I get that the x bar, the mean's 4, and I get that the standard deviation is 1.22, okay? If I took the time to convert each of these z-scores, each of these answers into a z-score, okay, and then I plot my answers along with their z-scores, okay, I'm going to get a plot that's going to look something like this. Now, this is going to be perfectly in a straight line because I made this a perfect, exact bell-shaped curve, okay? Now, how would you do this, though, on the calculator? Because you're not going to have to do this by hand, where you change things into z-scores and go plot it. Okay, what you would do on the calculator is you would take this set of data right here, and you would type all of that into L1. So I'm going to have you do that right now. I'm going to have you type this into L1. Let's see if I can pull this up here. Yeah, okay. So let's press Stat 1 for edit. If you have any old data in L1, move the cursor on top of L1, hit the clear button and the down arrow, it should wipe it clean, and enter all of those responses for the number of pets. 2, 2 3s, 3 4s, 2 5s, and a 6. Okay? Give you a second, type those into L1, and then I'm going to show you where the normal probability plot is located on your calculator. Okay? Again, the purpose of this is to try to estimate if the data set is approximately normal. Okay, once you have that in, you're going to go into stat plot. This is where you go if you were going to do a box plot or a histogram. You're going to choose plot line. You want to make sure that you tap enter over top of on. And then you can see there are 6 types of graphs here. Most of these you're familiar with. The one on the right kind of looks like a jagged, almost like line. That is the normal probability plot. So you want to select that last option. Okay? You want to come down where it says data list and make sure you're telling the calculator that your data is in this case, L1. So you're going to hit second and the number 1. So that says L1. And then, as we often do when we make graphs in statistics, we don't mess with trying to find a good window. We're just going to press zoom and option 9, zoom stat, and let the calculator do that work for us. Okay? Now, as you look here, you'll notice that looks pretty linear. Okay, I'm not seeing any curving happening at all here. Okay, no curves at all. So we're getting a nice linear pattern. That means the original set of data was in fact normal. Okay, you want to look for those hooks at the end if there's any type of skewness. Okay, all right. On the next page here, sorry. I have spelled out for you some screenshots for what you would do on the calculator if you were going to make a normal probability plot. Okay, I also have down here at the bottom another example. Is a pretty large set of data. It's asking, is this data set close to normal? I put this in my calculator already. I threw it into L2 previously. Okay, it's right here in L2. I just want to show this to you. I'm going to go back to plot 1. I'm going to keep it a normal probability plot, but change that my data now is in, L2. And I'm going to hit zoom stat and have you take a look at this one. Okay, again, this one also has a pretty linear feel. I'm not seeing any curves at all, so I would probably call this one approximately normal as well. And then we could move forward with doing normal CDF or inverse norm. Okay. All right, so to wrap up this section, I want you to flip to the last page here in the notes. I want to highlight a few just really important kind of summary things here that are located on this page for you that, at the end of this section, I'm hoping you guys are all comfortable with this. This notation right here, how to abbreviate the shape as being normal with the mean and the standard deviation. You should have memorized those percentages that are affiliated with normal distribution. You definitely want to make sure you know that if we're talking about z-scores, that's what a standard normal distribution is, that the mean is 0 and the standard deviation is 1. And then also here on the back, The different ways to check or assess for normality. Option 1, you could just observe the shape of a graph, a dot plot. You can check how well it fits that empirical rule, or you could make a normal probability plot by putting it into your calculator. Okay, there should be a group of problems here, maybe it was on the previous page, that you should be able to do to wrap up all of the problems here for this section 2.2.